everyone. My name is Loren Tate, and today myself and Michelle Downs will be giving you a presentation on the analysis of the Astrophysicist Collaboration Network. We analyze this network to optimize future collaboration between astrophysicists, and our presentation is Reaching for the Stars. So our group is a flock of SQLs. Our group members are myself, Loren Tate, Mikkel B., Michelle M., Michelle Downs, Chris, and Emily. So, to start, astrophysics stems from space science. And space science is a study of space with the use of chemistry and physics. So space has a lot of complexities to it, such as stars, planets, and galaxies, and the universe where it came from too. So one theory about where the universe came from and how it all started is the Big Bang Theory. And the scientists who study these theories are considered to be astrophysicists. So we can define astrophysicists as the scientists who study space with the use of chemistry and physics. A famous astronomer that most people are familiar with is Isaac Newton. He's most famously known for his laws of motion, one of them being, for every action, there must always be an opposite and equal reaction. So one thing that he did heavily in his research was he studied motion and how things moved. One of the big things that he studied was whether the sun was the center of the universe and the earth was the center of the universe. And he put to rest any doubt about the sun not being the center of the universe. So his conclusions from his research was that the sun was the center of the universe and the earth revolved around the sun. And the way that he came to these conclusions was by collaborating with Johannes Kepler's laws of planetary motion. So he really strengthened his research and came to the conclusions that he did by collaborating with another astronomer. Which brings us right to our problem statement, which is to determine the number of degree on the nodes, which are the astrophysicists, and assess which nodes should collaborate for future academic research. So in order to address this problem statement, we took our data set from Stanford EDU, which covered a time period of 10 years. This time period began in January 1993 and ended in April 2003. This covered basically the whole entire history of the Astrophysicist Collaboration Network. And within the data set, the nodes were representative of astrophysicists, and the edges represented a collaboration between those two astrophysicists. It did not matter how many times two astrophysicists collaborated with each other, and it didn't matter who collaborated with who, rather just if there was a collaboration between the two astrophysicists. And if there was, then there was an edge. So our edges were undirected and unweighted. So we first started by analyzing our data as a whole, and we realized that our data set was way too large to analyze as a whole. So in order to properly analyze our data set, we took a sample data set from our data set, and we assigned each node an identification number. And then we made our data set so that two identification numbers were in each row, and that meant that there was a connection between those identification numbers, or meant that there was an edge of collaboration. So then we took this data set and imported it into Atom, and we used the function len of nodes and edges to determine the number of nodes and edges. And in doing this, we were able to make meaningful conclusions about who should collaborate with who in the future in the Astrophysicist network. So the first part of our data analysis was to determine the degree centrality of each node. And degree centrality is defined as the number of current neighbors divided by the number of potential neighbors for the nodes. We calculated this because it gives us valuable information about the nodes and how to properly evaluate them. So in doing this, we imported the matplotlib and networkx packages, and the networkx package had the degree centrality function, in which we put the degree centrality function. We had a dictionary in return where the key represented the node and the value for the node was the degree centrality. And then we use the plot hist, H-I-S-T function to plot the histogram, as you can see here. And most of our nodes had a degree centrality of 0.1 and 0.2. So this meant that most of our nodes had a degree close to 0, which meant that the majority of our nodes did not have an important role in the collaboration network. And this is kind of where we started our data analysis. So now Michelle Downs will be able to give you some more information about our data analysis and conclusions. Thank you.
Thank you, Lauren. Let's continue on with some more visualizations of our data set by starting with the betweenness centrality. This is defined as the number of the shortest paths through a particular node divided by the number of shortest paths that exist between every pair of nodes in that graph. To plot this histogram, we imported the Matplotlib, PyPlot, and NetworkX packages. The NetworkX package provided the betweenness centrality function, which takes in the graph object as an argument and returns a dictionary in which the key is the node and the value is the betweenness centrality score for that node. We have used the plot hist function to plot the histogram of the degree centrality values. As you can see the results, very few nodes have high betweenness centrality scores, which means that only a few of our astrophysicists form an important path between collaboration with major astrophysicists in the network. Moving on, let's discuss some other visualizations for our data set. The first one we have here is the arc plot. It is a transformation of the node link diagram layouts. Using this graph, the astrophysicists are along the x-axis, and each arc represents how those nodes are connected. Next to the arc plot is the Surcos plot. It is a transformation of the arc plot by connecting the ends of the x-axis. This particular Surcos plot represents our largest click. And to find our largest click, we use the find clicks function under the NetworkX package to find each click. Among the clicks in our network, we have calculated the largest maximum click by using the NetworkX find clicks function and placing it within a sorted function. This click is represented by 14 astrophysicists, and in this click is a set of nodes that are completely connected by an edge to every other node in the set, which means that they're completely connected components. Lastly, we're going to talk about our conclusions. Our first conclusion is to find important collaborators. Using the degree centrality function in the NetworkX package, we were able to calculate the respective scores of each astrophysicist and then use that information to find the important collaborator. It was determined from our data set that the astrophysicist with the identification number 2022 is an important collaborator. Secondly, we recommend that our co-editors who have yet to collaborate follow the open triangle system. For example, if astrophysicist A has collaborated with astrophysicists B and C, yet astrophysicists B and C are not yet collaborators, then there's a good chance that those two can collaborate by using the triangle closure. From our results, we see that astrophysicists with the ID number 2022 and astrophysicists with the ID number 4159 should collaborate. Similarly, astrophysicist 2022 should collaborate with astrophysicist number 655. When we connect astrophysicist 2022 and 4159, the average clustering coefficient increases from 0.88 to 0.9. Which indicates that the node's neighbors are likely to be connected to nearly 90% of the node's other neighbors, which is relatively uncommon in a real data set. Next, we look at choosing two random pairs of nodes to connect. For example, 10603 and 5693, or 914 and 1468. We can actually get a reduced average clustering coefficient by making these connections and showing that these two researchers make an impact on the connectedness of the graph. With these recommendations, they will ultimately strengthen the robustness of the connectivity of the network. This is a visualization of the data set after we've made these collaborations. Thank you.